so many here who don't understand Finnish. So, my name is Tuomas Tauriala, Oscar Hotel 3 Echo Romeo Victor, and I would like to welcome you into this meeting on behalf of the RATS, or Radio Amateur Technological Society of Finland. So, Sappee is a great venue for these kinds of events. We have a good site here, high ground, which is nice for VHF and upper bands. But unfortunately, the main organizer, Erik, couldn't be here to have this opening speech because he's getting his 2 daughters here at the moment. So he will be here later today. And I think he'll want to say a couple of words tomorrow. So without further ado, I would like to welcome Dr. Kirsti Kauristie from the Finnish Meterological Institute. I tried practicing that word for a while there, but apparently it didn't help out any. But yeah, welcome Kirsti.
Okay, oh wow. Yes, so hello everybody. So I come from the Finnish Meterological Institute and my background is very much in basic physics. So I know nothing about engineering, so you can very easily with your questions make me embarrassed. So, but let's see how this goes. So my topic today is how GNSS, so global satellite navigation systems, can be used together with beacon receivers and transmitters to probe the upper parts of atmosphere, ionosphere, and how we can see also some space weather phenomena in the ionosphere with these instruments. Here is the contents of my talk. So first I will give you a brief kind of introduction to space weather. What does it mean, and how it appears, and why this topic is interesting. Then I will give very basics about wave activities and in ionospheric properties, both most likely very familiar topics for many of you. Then I will go more in detail about the research what we are doing in the Finnish Meterological Institute. We are probing the ionosphere with using a global navigation satellite system, and then we are putting up a network of beacon receivers, and we are planning to use both of them together. We have noticed, however, that global navigation satellite systems, so GPS, Galileo, GLONASS, they work quite nicely if you want to see the ionospheric phenomena at mid and low latitudes, but in high latitudes we have certain problems, and I will discuss them in more detail. And then finally, kind of a couple of slides about the future prospects and why this is interesting and important. Okay, so I start first about the space weather. The sun, like you know, it's emanating to its surrounding space light and warm, but also continuous flow of dilute gas which contains charged particles. This gas is called solar wind, and sun is not at all kind of stable. It has the sun surface has often eruptions, and these eruptions are associated with bursts in the solar wind, and these bursts cause rapid variations in the near Earth space, and these are then causing some problems technological systems. Here I have now an animation which I try to launch. Let's see how it goes. You can see how the things evolve. So we have sun here, and then we have there a kind of the surface, and you can see there is a kind of this kind of eruption. It is called solar flare, and in this kind of a flare, plenty of extreme ultraviolet radiation and X-ray radiation is emanated from the sun in a very rapid burst. Also at the same time, also some energetic charged particles leave the sun surface, and then also the disturbance in the solar wind leaves the sun surface, and these different kind of phenomena propagate in different velocities. They reach the near-Earth space. Here you see the, unfortunately not so very well, but you can see there is Earth and its magnetic field is there. The solar wind interacts with the Earth's magnetic field, and actually our magnetic field is shielding quite much us from the effect of this solar wind burst. It quite much deviates the energy from the burst around us so that it doesn't penetrate directly to our atmosphere. But on the other hand, it also causes some rapid variations here in the Earth, and along the geomagnetic field lines, part of the charged particles are directed to the atmosphere, particularly in the regions of nearby the magnetic poles, and interact with the atmospheric particles there. So this whole chain of these different phenomena is called space weather. Sometimes the solar bursts are very strong, and we get solar kind of so-called space weather storms, which may last a couple of days even. And during such storms, we can see auroras even in southern Finland. Typically, the interactions are kind of on a moderate level, and in those cases, we see auroras in Lapland or middle Finland. The space weather has kind of two phases, kind of Jekyll and Hyde appearance. So the beautiful part are the nice auroras, which people like to watch and also photograph nowadays very much. The other part, not so beautiful, is the problems what these rapid variations in the near-Earth space cause to various technological systems in the space and in the ground as well. Let's move forward. Here this figure summarizes these a bit not so nice parts of the space weather phenomena. Actually, this figure tries to summarize everything, these harmful effects which the space weather can cause. Maybe for your interest, the most interesting parts are those which are associated with the signal propagation. You can see there is kind of on the left-hand side of the plot, you can see these radio wave disturbances. You see the ionosphere there in the middle of the picture, and then some applications are using such frequencies that they get reflected from the ionosphere, and you can then nicely communicate over the horizon in the area between the ground surface and ionosphere. Then like you probably know, when you have a higher frequencies in the radio waves, then they go through the ionosphere, and then you can use these kind of systems like global navigation satellite systems where the signal is going through the ionosphere without very significant impact to the signal quality. However, sometimes, particularly when we have these strong space weather storms, the ionosphere is not at all homogeneous, but it can have kind of quite much spatial variety, kind of structuring, and the waves don't reflect from the ionosphere like expected, or even those waves which go through the ionosphere, they may suffer from scintillation. Then there are also other space weather phenomena. For example, as an example, these energetic particles which come from the sun, they can cause quite significant risk for the astronauts if they are outside the space station, for example. So, particularly for these people, it is very important to know that sun is calm and there are no eruptions or no particle bursts coming when they plan to do these extravehicular activities Also some electronics in different satellite solutions, for example in geostationary satellites, can suffer from these bursts of energetic particles. But for this particular talk now we concentrate to the effects in the radio wave propagation. Okay, now I will have a couple of very basic slides about waves. This is just to summarize the basic concepts about plane waves. So if we want to describe a plane wave, there are several parameters which are essential to describe the wave. So it is of course the amplitude, the intensity, then you may want to tell something about the spatial scale, so that can be characterized with the wavelength or wave number, and then about the variations in time, that's characterized with frequency, and then typically there is also then the phase. So if you are comparing two waves, there can be a phase shift between the two waves. You most likely know this much better than I do, but I'm giving just simple examples here. Talking about these electromagnetic waves, and this is a simple wave, this is propagating in the vacuum, and it is a plane wave, and it has a linear polarization. If we have this very simple case, then typically it is so that there is electric and magnetic field, and they are kind of perpendicular to each other, and they vary in a plane, which are perpendicular to each other, like you see from the picture, and the V notes to the V letter there tells the propagation direction of the wave. And these waves, they behave according to Maxwell equations. And as I have studied kind of basic physics, these Maxwell equations are very exciting for me. And these are the first things what we kind of learn in electromagnetics. And this slide just shows you the nice formulation of these Maxwell equations. You have the electric and magnetic field there, and then you have things like charge density. So if there is accumulation in certain regions of charge, that's linked with the electric field very deeply. On the other hand, the currents are defining the magnetic field. And then there are some parameters like permeability and permittivity, which describe the properties of the medium where the waves propagate. Then there are some mathematical operators called divergence and curl. And to characterize what these operators are about, I have there in the lower panel I have a couple of examples. In the left-hand side panel there is a vector field where the curl is very strong but divergence is 0, and on the right-hand side you see a vector field where the divergence is strong and curl is 0. So these formulations were kind of first invented, not exactly in this form, but the idea was invented in 1830 or late 1800 by a Scottish mathematician James Clerk Maxwell. Okay, so these are the rules which are followed in the ionosphere when the waves propagate there. Now I'm moving then to talk about the properties in the near Earth space and how waves propagate there. So like you saw from the previous slide, electric and magnetic fields and charged and currents, they are coupled with each other. So if one parameter moves, that has an impact to the others. Plasma is a name for a very dilute gas, where part of or significant part of the particles are electrically charged. So if these particles move, they carry currents, or if they accumulate, then this has an impact to the electric field. And In plasma, particularly these coupling projects are very pronounced. And consequently, if you have a plasma, for example, in the space or in the ionosphere, and you make a small disturbance there for some reason, this disturbance can quickly die out, but often can kind of start to grow very quickly, exponentially even, if the conditions are suitable for this disturbance. And often this disturbance kind of behaves so that they form waves. Plasma is the dominant state of matter in the space. So actually in the universe, 99.9% of the matter is in a plasma stage, actually. In the plots which you see on the right-hand side, unfortunately, the quality, you cannot see all the details, but in the upper panel you see the magnetosphere again, and the artist has tried to describe there how also at the boundaries of the magnetosphere there are often these plasma waves. On the lower panel you see actually they are real measurements of plasma instabilities, which are very often or quite systematically seen in the equatorial latitudes after the sunset. There you can get very complicated structures where kind of plasma is growing up, kind of less dense plasma bubbles are elevating to higher altitudes, and this is often causing some troubles, for example, to GPS signals or GLONASS signals. In the ionosphere, it is so actually that the plasma is not there alone. There is also the neutral atmosphere, and the neutral atmosphere particles, they are much heavier than the plasma particles, and the plasma is kind of interacting all the time with the neutral atmosphere where you have this oxygen and nitrogen. And that makes the kind of modeling the ionospheric plasma very complicated. So if we are talking about the structure of the ionosphere, like you most probably know, the ionosphere has 3 layers, which has been named F, E, and D, and there is some variability in these layers. So if you look at the right-hand side panel, there you see in the vertical axis you have the altitude, and on the horizontal axis you have the density of electrons, so number of electrons in cubic meter. You can see that the density is high at altitudes, or highest in the altitudes from 100 to 300 kilometers. The F layer, which is probably the most interesting for you, it is at the altitudes, let's say from 250 to 500 or so. And there you can see also some variability according to the solar cycle. So at the beginning, when I showed you this animation about solar activity, there is a certain 11-year cycle in the activity of sun. So we have been in a minimum in 2007. There was a solar minimum, so the eruptions were very rare, and now we are just a few years after the last maximum, which was some 2013 or so. Okay, so also in the F layer, in the ionospheric properties, there is some variability according to the solar cycle. And actually in the F layer part, the electron densities can vary with a factor of 10 according to the cycle. The day-night variations in the ionosphere are much bigger, so it can be even a factor of 100. The E layer, which is at altitude of 100 kilometers, that is the region where you see the auroras. And if there is very strong auroras, then the density in the E layer increases, and it can increase with a factor of 100. The Right-hand panel here just shows you the positive ions, which are kind of counterpart for the electrons. So usually, very much in the ionosphere, there is this charge neutrality, kind of neutrality applies. So always you have equal amount of positive and negative charges if you take a kind of gauge of plasma. And the dominant ions which appear in the ionosphere, there are O+, so oxygen ions, and then there is nitrogen or oxygen molecules and nitrogen oxide molecules charged of them. And when you go to higher altitudes, then the hydrogen ions start to dominate. And just to repeat what I just said, that in the F layer often the radio signals are reflect and auroras appear in the E layer, and D layer, which is the very lowest part of the atmosphere, there when there is a very strong solar storm with plenty of energetic particles, they can penetrate until to the D layer also, and in those cases the D layer can absorb radio signals. Okay, so if we are, okay, so the parameter what we are interested about is now the ionospheric electron density, because that is the factor which controls the radio wave propagation in the ionosphere. In this plot you can see what are the factors or the processes which control the electron density. If we take a gauge, one gauge, and see how the plasma density varies in this certain volume, here you can see the parameters which affect to the density. So first of all, you have the solar illumination. So if there is this extreme ultraviolet illumination, which is ionizing particles, and then consequently you get more charged particles. That's very important factor, particularly in the daytime ionosphere. Then you have the solar bursts, which I described. So if this burst hits the ionosphere, then there are also the impact of these X-rays, and then also the energetic particles which both increase again the electron density. In the night side, you can have the auroral particles. So the same particles which are causing the auroral luminosity, they can also increase the electron density. The plasma in the ionosphere is not at all kind of staying in the same place, but there is a global circulation pattern. So it's drifting slowly, forming actually a two-cell pattern in the polar cap. So if you are staying in one place, on the other side the plasma comes in, and from the other side it goes out. So this plasma drift is, if you're staying in one place, it is also affecting the measurements which you are doing. And then, like I said, the ionosphere is continuously interacting with the neutral atmosphere. The neutral particles and the charged particles are colliding and interacting with each other, and consequently also part of the charged particles get neutral, they lose their electrons or their electrical charging, and they become neutral particles. So these factors are those which affect to the electron content in the ionosphere. Okay, now I'm moving then about this business about measuring this electron content globally and regionally, and how the global navigation satellite systems, GPS, Galileo, GLONASS, how can they use to probe these ionospheric properties. Like I said, you at the beginning of this presentation, these GPS, GLONASS, and so on, they are actually used quite much, and quite much by the research community, and also by some other users who are interested by the ionospheric conditions. They use these dense GPS networks for probing the ionosphere. And like you probably know, so in GPS you have these two frequencies, L1 and L2, and both of them are kind of affected by the ionosphere when they go through the ionosphere. It is the path, the signal path is slightly deflected, not very much, not so much as in HF frequencies, but anyway, somewhat it is there is some kind of deflection or refraction, and the phase of the signal is changing, actually, so that when you are talking about the GNSS signals, you have the carrier signal and then you have the code. The phase of the carrier gets advanced and the code gets delayed. And actually using this effect and combining the L1 and L2 signals, the two different frequencies, in a certain elegant way which engineers have invented, you can extract the impact of ionosphere in the signal. And this, when you do make this linear combination of this L1 and L2, it's called LI, actually I like ionosphere. This can then be subtracted so that for the clients of GNSS users, they can provide information which doesn't have any impact or disturbances in the ionosphere. But for us who are studying the ionosphere, this kind of rubbish for the others is very good signal for us, because from there we can deduce the ionospheric content. And actually what you get from this signal is you get the electron density along the signal path. So it is integrated. So it is not, if the signal is coming directly above you, you get kind of the whole content through the signal, not just one point. And since GNSS has so many application areas, there are very dense networks of receivers, particularly, for example, in US. We have also in Finland quite nice network. In Japan, they have very dense network because they want to follow also the earthquake activity with these GPS networks. And with these dense networks and using this information about ionosphere, you can actually reconstruct a three-dimensional picture about the ionosphere. And that is done quite in a routine manner nowadays. Here you can see one example. This was a day from 2008, probably, I don't know, remember exact date, but on the left-hand side you see kind of 3D construction of our US, and then if you do kind of integration along altitude, you can derive this kind of a two-dimensional map of this three-dimensional volumetric picture. And these two-dimensional maps are often used in the ionospheric physics or in applications where you want to know how disturbed the ionosphere is. Okay. Now I'm moving then a bit to the higher latitudes. The GPS satellites and Galileo and GLONASS, they have the orbit inclination is 56 degrees. This means that the orbit is not exactly polar orbit, but it is a bit tilted. And if you have the receiver in the polar areas, it never sees the GNSS signal coming directly from above. It always sees it in the horizon in some region. And this is a bit problematic. So if you are seeing the GNSS signal in the horizon, it's then traversing very long distance in the ionosphere. And then if you want to kind of know exactly, then you get again the integrated electron density along this oblique path. And if you want to very accurately know what is kind of the structure of the 3D structure in the ionosphere, it is a bit difficult to construct from